Welcome everyone. We are in week 2 of the course Basics of Mechanical Engineering 2, where we are studying manufacturing processes. In the 2 weeks, we have studied about the basic introduction about engineering materials, and we talked about the packing fraction, atomic structure, and crystal structure, and the phasor diagrams that which are there when we have alloys with us. So this session that I am going to take now is a tutorial session on what is discussed in the previous lectures. So this will be a tutorial session on the iron carbon majorly phase diagrams and atomic packing factors. Let me talk about the atomic packing factors. Just recall the concepts that we studied in the previous lecture. So this is a table representing the different elements and different parameters which are associated with different structures. For simple cubic, A naught is equal to 2R, where A naught is the edge length, this is A naught, and R is radius of the cell. So this is what I am representing here is BCC. So here for simple cubic, A naught is equal to 2R, number of atoms per cell is 1, because total 8 edges would have the part of the cell, and when we combine together it becomes one cell. Coordination number is 6, packing factor is 0.52. An example for this could be polonium, that is one of the metals, and alpha manganese as well. Second is BCC, for which A naught is equal to 4 by under root 3 R, number of atoms per cell is 2, coordination number is 8, packing factor is higher, that is 0.68. Examples are iron, titanium, tungsten, molybdenum, and so on. For phase center cubic, the A naught is related to R as 4 by under root 2 R, number of atoms per cell is 4, coordination number is 12, and packing is more dense here, that is 0.74. Iron, carbon, gold, silver are examples of this. Then HCP is also one of the structures of the crystals, where alpha is equal to 2R, number of atoms per cell is 2, coordination number is 12, and packing is here as well 0.74. Titanium, magnesium, zinc, beryllium are the examples. Let me directly come to the problem statement and let us try to solve it. The statement says an element has body centered cubic crystal, that is BCC, with a cell edge of 300 pm. The density of the element is 8 grams per centimeter cube. How many atoms are present in 200 gram of the element? It is so simple here. We know that the volume of unit cell is equal to A cube, where edge length A is given here, 300 picometers, which is equal to 3 into 10 raised to power minus 10 meters. Because other unit is in centimeter cube, I will also put this in centimeters. This is equal to 3 into 10 raised to power minus 8 centimeters, which gives me my volume as 3 into 10 raised to power minus 8 centimeter cube. 3 cube is 27, and 10 raised to power minus 8 goes as 10 raised to power minus 24 centimeter cube, or I can put it as 2.7 into 10 raised to power minus 23 centimeter cube. This is my volume. So total volume of 200 gram of element is given. Total volume of 200 gram of element, this is equal to mass by density. This is equal to 200 grams is given here, and density is 8 grams per centimeter cube. Grams per centimeter cube. So this gives me 25 centimeter cube. Simply to find the number of cells, we will say number of unit cells is equal to total volume of the element by volume of the unit cell, which is equal to 25 by 2.7 into 10 raised to power minus 23, which is equal to 9.259 into 10 raised to power 23. Now, because it is BCC, so therefore, total atoms present is equal to number of unit cells into 2. This is equal to 9.259 into 10 raised to power 23 into 2. This gives me my answer as 18.518 into 10 raised to power 23 atoms. This was simply for the body centered cubic. Let me see another problem statement for the face centered cubic crystal structure with a cell edge of 200 picometer, density as 10 kilograms per meter cube, and the number of atoms present in 0.5 kg of the element are required. This will go in the same way as we did the previous numerical, only the point is here it is face centered cubic, and when we say face centered cubic, total number of atoms per cell is 4. We will multiply it by 4. So, you can try to solve this problem by yourself, and I am just putting the answer here that we will get 2.5 into 10 raised to power 28 atoms. It will go in the same fashion as we did the previous problem, only the face centered cubic has 4 atoms per cell. So, whatever mass you get, number of unit cells will be multiplied by 4. Unit cells into 4. This gives me this answer. Let me come to the phase diagrams. Just a quick brief recall of the terms. Phase diagram, the term phase diagram describes an homogeneous mass of material such as metal in which the grains all have the same crystal lattice structure. Example, in brass, zinc is dissolved in copper. So, phasor diagrams, so these are the cooling or which are being represented here. So, it is cooling, and this is the point, that is the freezing temperature where the liquid turns into solid. It is liquid here given, it is solid here, and this is a mixture of liquid plus solid as it is given. So, this you have also seen in the previous lectures. Kinds of the phase diagram, if we say unary phase diagram, this is for water only. It is ice, water and steam, that is solid, liquid and gas, 3 states, and this is a triple point where all the 3 exist in unison. Binary phase diagrams are there, which have 2 components. These phase diagrams have 3 different categories. Category type 1 is the material which are completely soluble in the liquid as well as in solid state. So, this is an example of the binary phase diagram type 1, that is copper and nickel, where percentage weight of nickel is presented from left to right, and this is a complete soluble. You can see it is shown here, it is a liquid here, it is liquid plus solid, it is a complete solid here. So, materials which are completely soluble in the liquid as well in solid state, that is presented in the type 1. Then comes the binary phase diagram type 2, the material which are completely soluble in liquid state, but partially soluble in the solid state. This is why we have the eutectic phase diagrams. Alpha phase is the solid solubility of tin in lead, and beta phase is the solid solubility of lead in tin. So, here lead and tin is given, and this is the percentage weight of the tin from left to right, that is being shown here. At 61.9 we have our eutectic phase or eutectic reaction. This is liquid, this is alpha phase tin, this is beta phase lead, and here we have alpha plus beta existing together. Then comes type 3, the materials which are completely soluble in the liquid state and completely insoluble in the solid state. So, this becomes my type 3, and this is an example of the bismuth cadmium, where we have liquid here and here we have the reaction, and bismuth and cadmium mixture exists here in solid state. So, they are completely insoluble here. Then comes a quick review of the iron carbon diagram. The pure iron on a peat, as it is discussed that upon heating pure iron experiences many changes. We have ferrite, that is alpha iron is here, we have austenite here, we have ferrite plus cementite that is existing here, we have eutectic reaction, we have eutectoid reaction. The eutectic reaction is at the temperature 1147, it is given here, and at 4.3% of the carbon, where liquid turns into austenite plus cementite. Eutectoid reaction is at 7 to 7 degrees centigrades at 0.76 percentage of carbon. Solid turns into two different solids, that is our austenite here turns into hypoeutectoid and hypereutectoid solids here. Hypoeutectoid here is perlite plus ferrite, hypereutectoid is perlite plus cementite. So, this is our iron carbon diagram. Based upon this, let us see some problem statements. This is a problem statement for a 99.65 percentage weight of the iron, 0.35 percentage of carbon alloy at temperature just below the eutectoid. Determine the following. It is 99.65 percentage of iron, 0.35 weight of carbon. That means, we are almost here, 0.35, almost here, right. So, it is telling below eutectoid determine the following: the fraction of total ferrite and cementite. It is asking fraction of pro-eutectoid ferrite and perlite, fraction of eutectoid ferrite. Now, because it is 0.35 is less than 0.76, as you can see here, we are here in the hypoeutectoid phase. That means, hypoeutectoid phase is being talked about. So, in case of hypoeutectoid steel, the final micro constituents we can get alpha dash, that is pro-eutectoid ferrite, we can get alpha E, that is eutectoid ferrite, then we have alpha, that is total ferrite, this is total ferrite, that is the sum of the above two, it is alpha E plus alpha dash. Then we have cementite. So, we are now going to talk about the two phases as per the problem statement that is given, that is possible combination of alpha dash, alpha E and Fe3C. They are talking about ferrite and cementite and pro-eutectoid ferrite and perlite. So, we will talk about the problem 1 first, problem A, ferrite and cementite. A is ferrite and cementite. To get this ferrite and cementite, that is alpha plus Fe3C, let me see that we are here at 0.35 percentage of carbon. right, and we need to see the cementite, and here we have ferrite. So, here percentage of carbon is 0.22. For the cementite, it is 6.67 percentage of carbon. So, using the tie line rule, it gives me fraction of ferrite as the composition of cementite minus composition, that is, I will say desired, over composition of cementite minus composition of alpha. So, this is equal to 6.67 minus 0.35, that is the desired one is here, for the composition of interest, that is 0.35, which is given in the problem statement, by 6.67 minus 0.022, it is 0.022. So, this is equal to 0.95. This is fraction of ferrite. Now, again this is also asking fraction of cementite. Fraction of cementite, this would be 1 minus fraction of ferrite. This is equal to 1 minus 0.95, that is equal to 0.05. Or we can also calculate fraction of cementite using a tie rule. Using tie line rule, we can also put it as 0.35 minus 0.022 by 6.67 minus 0.022. This will also give me 0.05, right. These are both same. Now, next point they have asked is fraction of proeutectoid, ferrite and pearlite. Fraction of proeutectoid, ferrite and pearlite. Now, what is pearlite? It is alpha E plus Fe3C, that is ferrite plus cementite. So, here when we say proeutectoid, I will draw the tie line here. We have 0.35 percentage here and we have pearlite here, that is 0.75 percentage of carbon, and proeutectoid, because we are talking about, we will talk about proeutectide ferrite here. Proeutectide ferrite, which is equal to 0.022 percentage of carbon. Simply using the above rule, fraction of proeutectoid ferrite, that is alpha dash, is equal to 0.76 minus 0.35 by 0.76 minus 0.022 is equal to 0.56, that is the fraction of proeutectide ferrite in the alloy. Then fraction of pearlite, that is alpha E plus cementite. This can again be taken using the tie line rule from 0.35 to 0.022 and the total, that is 0.76 minus 0.022. So, essentially this blue line is my fraction of perlite in the total. Total is this red line that is all given, right. So, this is my fraction of perlite, and I will put another color. The green line is my fraction of pro-eutectide ferrite. This is green color and this is blue color. So, this value comes to be 0.44. I can write it here. This is 0.44 and the remaining one, that is 1 minus 0.44, this is 0.56. So, we can keep calculating anything that is asked. Now, the third part is fraction of eutectide ferrite. Fraction of eutectide ferrite, when they say fraction of eutectide ferrite. Now, eutectide ferrite is calculated using the total ferrite. We have seen in the previous slides that total ferrite is equal to pro-eutectide ferrite plus eutectide ferrite, that is alpha is equal to alpha dash plus the eutectide ferrite, that is alpha E, that is 0.95, that is calculated, and 0.56, that is also calculated, and alpha E is our now point of interest. Here I get alpha E is equal to 0.95 minus 0.56. This is equal to 0.39 alpha E. Now, again one point I would like to mention here is that since this 0.39, that is alpha E, is also less than 0.76, we can give a statement that it is a constituent of hypoeutectoid steel. So, again you can see it is hypoeutectoid only once again. 0.39 also lies somewhere here, right. Constituent of hypoeutectide. Okay, there is another problem statement which I will leave it for you. In the iron cementite phase diagram, that is iron carbon phase diagram, the eutectide composition is 0.8 by weight percentage at 725 degree centigrade. The maximum solubility of carbon alpha ferrite is 0.025 weight of carbon. Steel sample having no other alloying element except 0.58% of carbon is slowly cooled from 1000 degrees to room temperature. Find the fraction of pro-eutectide alpha ferrite in the above steel sample at room temperature. Since we are now talking about a temperature that is more than 725 degrees, that is we are talking about austenite, it is gamma. So, here at 725 degrees austenite converts into ferrite, that is alpha, plus cementite, that is Fe3C. So, we can again keep using the lever rule or tie line rule. I will put it here. This is tie line rule, or we also call it as lever rule. So, this I leave it for you to solve. Just make sure that the CO composition, that is of our interest, or we will say CD, C desired, that is 0.5% weight, that is given here, and the ferrite composition that is given is C alpha, that is 0.25, and the eutectoid composition that is given here is, I will put it at CE, at eutectoid is 0.8. So, you can draw a tie line here, this is 0.5, 0.8, 0.25, and then try to calculate or find the fraction of the pro-eutectide alpha ferrite in this. I will just give you the solution. The answer is 0.387, or we can say 38.7%. 38.7% of pro-eutectide alpha ferrite in the steel is present at the room temperature. Room temperature, right? Try to solve it, please. Another problem statement is there that is asking about the name of the phases and their fractions at equilibrium at the following temperatures just above 1493. Just above 1493, what does exist? Just below 1493 degrees, what does exist? Just above 725, just below 725. You know, different researchers keep on telling this as different temperatures. Some people say 725, some people say 727. So, whatever is given in the problem statement, we will do accordingly. And next problem is, what is the fraction of the pro-eutectide cementite at 1.4% carbon and 1% carbon. This also you can simply solve. So, 1493, if you know or if you remember, 1493 is the point where our delta ferrite exists. So, this is what they are asking. Here we have delta ferrite at 1493 degree centigrades. Then above this, what is there? Below this, what is there? This we all know, using lever rule only we need to calculate this. Above this, what is there? Only using lever rule. If you wish to put it here, I will just give you some hints so that solve this problem. Using lever rule, we can just put here, this is 0.2, and here we have liquid, here we have delta ferrite. From 0.2 we have 0.5% here, and this is 0.1%. Just calculate the fraction of the delta ferrite. So, this is of your interest. Also, similar is for the 725 degrees, where majorly eutectic reaction is there, eutectoid reaction is there. So, for eutectoid reaction, you have to use this as 0.8%, 0.2% and 0.022%, right. Just to recall, we have alpha ferrite here, we have austenite here. Similarly, on the other hand, for the complete line, we have, if I say alpha ferrite here and if I say cementite this side, from this you can just recall that we are talking about cementite, that means 6.67% would come here, and the 6.6 percentage is on the right side. On the left side we have the alpha ferrite, that is we have 0.022, in between we have 0.2. So, this will also give you the fraction of the alpha ferrite and cementite. These all you can calculate. So, what is the fraction of polyductite cementite at 1.4% and 1%? This also you can use the lever rule while putting your percentage of interest, that is 1.4% here, and then between 0.8 and 6.67%, that is polyductite phase you are talking about. Right, that is given here. This you can calculate, and similarly you can calculate for the other problem, that is for 1%. Just calculate all these so that you have better practice and try to understand how does the phases change. So, these were majorly I have been discussing the iron carbon diagram. These are the percentage changes when a liquid transforms into a solid, or what is the percent, like for example, when you learn casting in the next week. In the casting, liquid solidifies, then what is the need of riser, what is the need of sprue? These are different components or the parts of the mold system that is there. There you will understand what is the need of the understanding of the phasor diagrams or metallurgy, and what kind of heat treatment is required later when we do certain machining, when we try to do some surface case hardening or so. Those all things would be applicable in the further weeks when we will study. We have discussed about the iron carbon phase diagram majorly in this week in the previous lecture. I will give you one problem of another phase diagram. Let me see, this is a lead tin system where they are asking to determine the fraction of phase in an alloy of 80% of tin at 184 degrees centigrades and 182 degrees centigrades. In lead tin what happens? So, I have lead at left side and tin at right side. So, this is 100% lead or 0% tin I would say. So, tin percentage is 0 here, it is 100. Oh, this is percentage weight of tin. And for the temperatures at 183 degrees, and 18.3% of the tin, we have the alpha, that is the tin converting to the liquid phase. This goes till 327 degrees centigrades, and here we have the eutectic reaction at 61.9 percentage of tin and till 97.8, it goes just like this, and then we have at 232 degrees centigrades where we have the solid tin phase, and this keeps on going down. So, here we have from here this is liquid, this I will say alpha plus beta, this is only alpha, this is only beta. Here we have alpha plus liquid, here we have beta plus liquid. Now, the point of interest they have asked, this I can also further label here, this is 100 degrees, 200 degrees, 300 degrees. Right, and this is because 0 to 100 tin, I could divide them into certain parts. For example, here I have 50% of tin and 50% of lead. Now, the point of interest that is given in the problem statement is it is at 184 degrees centigrades and at 182 degrees centigrades, what happens? That means 184 is here, this is exactly 183, this is 183, above this is 184 degrees centigrades, below this is 182 degrees centigrades. Predominantly is asking above this eutectic reaction line, what is above and below this? At 80% octane. So, at 80% octane. This also I am leaving it for you. You can use lever rule to determine the compositions above and below 183 degrees. That means, you would have to find at 184 degrees what is there, then you will find also calculate at 183 degrees what is there, and we will calculate for beta phase. Right. This problem would be solved here. In the lecture notes, you will find the complete solution, but here I am leaving it blank for you to practice this. With this, I am closing this tutorial session on the week 2, that is metallurgy and atomic packing fractions that we have discussed here. We will meet in the further weeks and discuss more about the manufacturing processes in the course Basics of Mechanical Engineering 2. Thank you.